Look up on a clear night, and the stars seem perfectly still, a quiet, fixed canopy hanging over the Earth. But that stillness is an illusion. Out there in the dark, galaxies are colliding and stars are detonating as the entire universe expands in every direction at once. We will never build a spacecraft fast enough to reach these deep space objects. So how do astronomers measure the velocity of something they can never touch? The answer starts with a local, everyday experience on Earth, the sound of a passing ambulance. You can hear the pitch drop as the ambulance drives away. This happens because the sound waves are being physically stretched out by the vehicle's movement. This is the Doppler effect. The same mechanical rule governing sound waves in a city street allows us to decode the movement of the cosmos. Light travels in waves just like sound, and it is subject to the exact same stretching and compressing mechanics. When an object in space moves toward us, its light waves compress into shorter wavelengths. This shift toward the shorter end of the spectrum is known as blue shift. Conversely, when an object moves away, its light waves are stretched. Because red light has the longest wavelength in the visible spectrum, this stretching physically shifts the observed light toward a red hue. By analyzing this color shift, astronomers can definitively prove whether a star is approaching Earth or pulling away. In 1929, astronomer Edwin Hubble used the massive telescope at Mount Wilson to look deeper into space than ever before. He spent his nights painstakingly cataloging and separating the faint light arriving from the deepest reaches of the sky. Hubble's targets were distant galaxies, enormous clusters of stars sitting millions of light-years beyond our own. He expected a random mix of colors, but instead discovered a massive anomaly. Almost every distant galaxy he observed was redshifted. Hubble deduced two facts. Nearly all galaxies are moving away from Earth, and the further away they are, the faster they are receding. This observation provided the first empirical proof that the universe is not static. It is expanding in all directions. But what physical force is actually pulling these galaxies apart? Some of it is relativistic redshift, the local movement of an object through space relative to Earth, like a star drifting away. But the expansion Hubble saw is driven by cosmological redshift, where the objects aren't moving through space. Instead, the space between them is growing. As light travels through the universe, the fabric of space expands, stretching the light waves along with it. There is also gravitational redshift, which occurs when light loses energy and stretches as it attempts to escape a massive gravity well, like a black hole. While local movement and gravity play their roles, cosmological redshift is the dominant force driving the expansion of the distant universe. To translate these red hues into hard data, astronomers use a mathematical variable called z. This is calculated by comparing the wavelength of light a galaxy originally emitted against the stretched wavelength we observe on Earth. A positive z proves redshift and recession, while a negative z indicates blue shift and approach. Applying this equation across the night sky allows astronomers to calculate the distance and velocity of everything we can see. By measuring redshift, we are looking backward through time. We are mapping the current scale of the universe and the rate of its growth since